Hi, this is ET250 Lecture 24 Part A. This is going to be a two-part lecture. In the first half, we're going to cover just the Z equivalent for six different combinations. The first two will be RC in series parallel, then RL in series parallel, and then this interesting one, LC in series in parallel. In the second half, we'll cover a power factor correction example where we will look how to solve for a capacitor, a power factor correction capacitor, two different ways, and we'll look at simulations for all of these things. Okay, so let's begin. So this is the combination of inductors and capacitors and resistors that we will look at. Series, parallel, series, parallel, series, parallel. And I want you to recall that we are going to talk about the voltage across all of it and the current through everything, and that Ohm's law or complex Ohm's law will be the Z impedance is equal to the magnitude of V over I. So bigger Z means less I for the same voltage. Then also I want you to remember that the theta Z is the same as the phase difference between V and I, the overall voltage and current. So if the phase difference is positive, what it means is that the current is smaller, has a smaller phase, so it's lagging the voltage. If this is negative, that means this current is leading the voltage, okay? And we will analyze in the simulation how frequency changes this behavior. All right, so let's look at a resistor and a capacitor in series. The nice thing about all this phasor stuff is even though everything is AC, everything's oscillating up and down, we can treat everything like resistors. So if we look at the impedance for R and C, we just add them up. We replace them with our known formulas, R and 1 over j omega C. And we can see here that the J going upstairs will result in a negative. So this is the rectangular form of the equivalent impedance for a resistor and capacitor in series. So this is the real part here, and the negative 1 over omega C without the J is the imaginary part. Okay, what about the polar form? Well, we can do the Pythagorean theorem on this to get the magnitude, and then the inverse tangent of the imaginary over the real. Okay, so this and this is the, we got the magnitude here, Pythagorean theorem, and the inverse tangent for theta z. Okay, so these are the equations, r squared plus 1 over omega c squared square root and inverse tangent of negative 1 over omega rc. Note I pop the R back in there. So what kind of intuition do we get from this? You know, I hope you realize by now I'm a big stressor of intuition, not to just show you the equations, but I like to show you exactly what each term means, right? And so for low omega, what does that mean? At low frequency, what does the capacitor behave like? It behaves like an open circuit. So that means the capacitor is much more dominant, right, at low frequency. And an open circuit means the impedance is going to go to infinity. Now, is that true from the math? Can we see that we get a correlation between the math and our intuition? Well, as omega slows down, what happens? This small number here actually blows up because it's in the denominator. And sure enough, this whole thing goes towards infinity. Good. What about the phase? Well, if we recall from our inverse tangent understanding that tan inverse of x gives you this, right? Here's x, and I believe it does this, 90 and minus 90 degrees. What do we get going on? We have that the as omega gets bigger, we actually go down this way. So we get closer and closer to minus 90 as omega gets bigger. But as it gets smaller, what happens? Sorry. As omega gets bigger, we get this thing going to 0, which is here. But as we get smaller, omega, 1 over omega actually gets bigger in the negative direction. So a low frequency means this explodes to negative infinity going that way, which means the tan inverse goes to negative 90. And if we recall, a pure capacitor also has a negative 90 where the theta I leads the theta V. Good. What about in the opposite direction? What if we increase the frequency? And what do we mean by increasing the frequency, just in case anyone's lost? Well, the voltage and current, remember, this is all AC system. If it oscillates faster and faster, that's what we mean. That's what this omega is, right? So that omega increases, now this guy goes to 0 and you get square root of R squared. Well, that's just a resistor. And that's what we would expect because the capacitor essentially turns into a short, right? Now, what about the phase? So as omega gets very large, this thing goes 1 over a large number, which goes to 0. Tan inverse of 0 goes to 0. And so now you have theta I and theta V in phase. Okay. And so we should say here, steady state capacitor. And here we could say high frequency capacitor. And that behaves more like a short. Okay, good. Let's look at the simulation and see if we get a similar result. So let's go over here to the simulation and let's see what we got. So here's a simulation of a resistor and a capacitor in series. And do we get the same theoretical and intuitive matching? And let's double check. At low frequency, what do we have? We have the current leading the voltage by 90 degrees. Perfect. More capacitive. And we have a small overall current. Now, as we increase the frequency, what do we notice? The capacitor behaves more and more like a short, and you can see the amplitude of the current increasing. What you can also notice is that the current becomes more and more in phase with the voltage, right? I rewrote the equations here just so you can see it. And all these simulations are going to be in the description. So please check those out on your own time and get, play with the numbers and get some more intuition. Okay, good. So this is kind of what's going on. You can see the current in yellow here moving much faster than the ones over here. All right, so let's stop this and go back. So let's go to the second one where the resistor and the capacitor are in parallel. So when they're in parallel, we can use our parallel formula, ZR/ZC over ZR plus ZC. We can punch in these guys. Now we've done this in a previous lecture, so hopefully this is not new. And we can multiply a little trick, the top and bottom by j omega c and get this, R over j omega RC plus 1. Now, if I want to get in polar form, what do we have? Oh, sorry, rectangular form. I can multiply the top and bottom by the complex conjugate of the denominator. Another little trick. And what do we get? All real on the denominator, right? That's nice. And you get R minus j omega R squared C. Don't forget that R. And then on the bottom, you get 1. And then you get a minus j squared, which is a minus minus, which is a positive. Omega squared R squared C squared. Well, what happens to the cross terms? Don't forget, they cancel out. You get a plus and a minus. So this is pretty easy to write the rectangular form now. It's this guy here, R over the denominator, and minus omega squared C over the denominator. This is the imaginary part without the J, and this is the real part. Easy. What about the polar form? Well, we can go back to this one here. And if you recall from the polar form, we can say, take the numerator, make it polar, and then take the denominator, make it a polar form. We have R over the Pythagorean theorem of the bottom, which is this. And we have 0, because that's a phase of 0, minus, because we're dividing phasors, inverse tangent of imaginary over real. So minus, that's where that minus comes from. And you've seen this before, but I hope this is a good refresher. All right, so what about the intuition again? What's the intuition? Well, let's look at here. At low frequency, this is going to become like an open. So that means the resistor is more dominant at low frequency when this is in parallel, as opposed to this one where the capacitor was more dominant, right? Okay, so what else? At high frequency, this is more like a short. So the capacitor is more dominant at the high frequency than the resistor. Do we see that from the math? Do we see that from the derivation? Okay, do we see that this becomes more like a resistor at low frequency? Well, let's double check. At low frequency, check it out. That guy goes to 0. And sure enough, you get R over 1. Yep, that goes to a resistor. What about the phase? Well, if we go here and if the frequency goes to 0, you get inverse tangent of 0. Doesn't matter if it's positive, negative, you're at 0 here. And yep, that becomes like a resistor. At high frequency, let's see if it becomes more like a capacitor. Well, at high frequency, what do we get? We get essentially R over an infinite number. So that becomes what? 0, right? Okay, so low impedance is like a short, high current's going to go through here. And then what? What about the phase? So at high frequency, you get inverse tangent of this large number, which means you get 90, but then you slap on the negative, you get minus 90, right? And so, yep, that's like a capacitor where the current leads the voltage. Excellent. So let's see if this is true on the simulation. Go back to here, share screen. And so here's a resistor and capacitor in parallel. Notice I put a little 1 milliohm resistor here just to make sure everything numerically balances out. I have the equations written up here just so that you can see them. But if I run this, look what's going on. At the low frequency, we notice it's more resistive because the capacitor is acting more like an open, and the current and voltage are in phase. But we have a small current because it's only depending on the resistance to impede current. As we go to a higher frequency, what do we notice? We notice that all the current, or not all, but a lot more current is flowing through that capacitor because this is behaving more like a short. And we can see that the current, if I pause it, you can see that the current is leading the voltage, right? And that's a more capacitive behavior. We also see that the amplitude of the current starts increasing with increasing frequency because everything now starts going through that capacitor. This should be very similar to your lab that you guys saw in lab 10, where you saw the S increase because the I increased even though the V stayed constant. And the power P is going to stay constant because the V across that resistor is going to stay the same. Good, so just another shot looking at this resistor and capacitor in parallel. Great, so let's go to the next one. Okay, so let's go to an inductor and a resistor in series. And again, you just add them up, but this time you're going to use j omega L for the inductor. And when we add these up, this is probably the easiest one because look, you're already in rectangular form, no tricks, no divide by, anything, right? So that's the real part, and this is the imaginary part, just the omega L. Fantastic. What about the polar form? Well, Pythagorean theorem and inverse tangent of omega L over R. This is probably the simplest one we're going to have to deal with, a resistor and inductor in series. And fortunately, we model a lot of motors like that. So that's kind of nice. All right, what else can we see? We see that the inductor and the resistor have behaviors at low and high frequency that we can intuit. And so at low frequency, remember the inductor is behaving like a short, that water wheel behavior. Okay, and so it's actually becoming more resistor dominant, right? Because if this is just a wire, it's just like a resistor at low frequency. Let's see if that's true from the math. So at low frequency, look at this, omega goes to 0, you're just left with square root of R squared. So that means the magnitude just goes to R, easy. What about the phase? Well, at the phase, if I just look at here, I get a 0 in here. So inverse tangent of 0 becomes 0. So I get theta I and theta V in phase behaving like a resistor. Fantastic. What about at high frequency? At high frequency, we can look at the gain in phase and go, okay, well, what's going on? At high frequency, this goes to infinity, and that should make sense because this water wheel does not want to change its direction very fast, especially if you're shaking it quickly. So the impedance jumps up to infinity, right? And what about theta Z? Well, we know that this inverse tangent creeps up to 90 degrees, right? So when this omega goes very high. And what does 90 degrees phase mean? Theta I lags theta V. That means theta V is greater than theta I, right? Good. And so this is what we should see for this circuit. So let's again go to the simulation, see what we get. Okay. So we go to the next one. We got a resistor and inductor in series here. Let's run this guy. And let's see what we have at low frequency. Look how there's a lot more current because the inductor is behaving like a short. And look how the current and voltage are in phase, right? And we get a large amplitude for current. Now, as we start increasing the frequency, what do we notice? We notice the current lagging the voltage. Perfect. And we see a smaller amplitude and current. And again, I have all the equations written out here. Please check out the description, click on those links and play with these, right? Okay, good. So hopefully you're getting a sense of what's going on. Now let's look at the next one where we have the resistor and inductor in parallel. So what does that look like? So with the resistor and inductor in parallel, again, we use the parallel formula. R times j omega L over R plus j omega L. Again, the trick, now we have some weirdness. What do we have? R minus j omega L, R minus j omega L. We multiply it by the complex conjugate of the denominator, just a little easy way to make the denominator all real, okay? And so what are we left with? R squared, j omega L, good, minus j squared, which is positive, then R omega squared L squared. Great, that's the numerator. And the denominator is R squared. And then we got a minus j squared, which is positive, and then omega squared L squared. Good. So this is the imaginary part and this is the real part. So the real part is r omega squared L squared over this denominator. And then the imaginary part is r squared omega L over that same denominator. Good. And so this is the imaginary part without the J. This is the real part. Fantastic. Now, what about the polar form? Well, polar form, I look at like this guy and convert it into their two polar forms. So I go, well, that's r omega L with an angle of 90 degrees. Okay, that's not bad. And I would look at this and I would say Pythagorean theorem with an angle of omega L over r. So I would get this, right? These would be my polar form. And then if I divide phasors, I subtract the phase. So this is the phase 90 minus this guy, and this is the magnitude, full stop. Okay. Looking at this, I go, all right, I have a resistor and an inductor, and at low frequency, again, this inductor behaves like a short. So this actually kind of gets nixed out if this becomes a short. Right? So it's more inductor dominant at low frequency. Do we see this? Do we see that we get low impedance, right? Let's go to the magnitude. At low frequency, what do we see? We see that, well, the denominator goes away, just r squared square root, but that top completely goes away because this omega goes to 0. So Z equivalent goes to 0, which is going to be like a steady state inductor or short. Excellent. Well, what about the phase? Well, the phase says here that omega is going to be nearly close to 0. So that means this whole guy goes to 0, which means you're just left with 90. So that means that theta I lags theta V, and you have a more inductive situation. Good. So low frequency acts like an inductor. What about high frequency? High frequency, this guy's going to behave like an open, doesn't like to shake, and all the current's going to go through the resistor. So it should be more resistor dominant. So let's check that out. When omega is very large, what do we get? This is a little tricky, right? This is a little tricky. So we know that this omega L squared term is going to dominate the r squared in the denominator. So it's almost like this r squared kind of goes away when omega gets very, very large. Okay, so you're left with that. I'm just covering it with my finger and I just wrote it here. Okay, so negligible, right? That r squared is negligible. I should even say r squared is negligible. All right, so then what do we see? We see a square root of omega L squared. Well, that's just the same as omega L. They cancel out if in the limit, and we're left with R. Fantastic. So at high frequency, it behaves like a resistor because this guy goes away, and you can see that mathematically. Man, those limits are useful from calculus. Like it's like they we're trying to give you guys tools that you'll use later on in life, or at least in your academic career. Okay, so then what? Let's look at the phase. As omega gets larger, what do we have? We get 90 here, right? Because a large X means you get 90. 90 minus 90 gives you 0. Fantastic. And we get a more resistive situation where theta I and theta V are in phase. Now, I wanted to highlight something while we got this real and imaginary. It's very tempting, a common mistake where you'll look at the circuit and say, what's the real part of that overall impedance? And it's so tempting to say that that's R, right? But we note, look at this. I'm actually going to circle this. And we're going to put a note here. Note, not R in this case. However, in the series case, it does happen to be R. Here it is R, right? Let's look back to the capacitor case, and maybe I need to put that in there. So in the capacitor case, it's the same thing. Look at this real part of Z equivalent when these guys are in parallel. This is note, not the resistance. It might be tempting, but it's not. But in the series case, check this out. If I go back here, it is R. Okay, so just don't get that twisted when you guys are, don't make a wrong assumption is what I'm saying. All right, let's go to the simulation and check this out. So we have here the resistor and inductor in parallel. Again, I put a little resistor here just to make sure everything settles out nicely. And I'm going to run this guy, and notice at the low frequency, the inductor is behaving like a short, and most of that current is going through that inductor. And look at the current; it's lagging the voltage, so it's very inductive. And look at this current, large amplitude. As I increase the frequency, now we're dependent on the resistance because the inductor is behaving more like an open circuit, and now the current's going through the resistor. So the resistor is what impedes the current flow. And notice we have a smaller current here, and then this is kind of in between. Okay, And so you guys hopefully can see that visually with the dots and through the graphs. And again, I put all the equations here so that you guys can see it. Okay, let's go back and check out the fun ones, LC in series and parallel. Okay, so for an LC in series, this one you really got to put your thinking cap on and really kind of hone in. So if you have an inductor and a capacitor in series, it's the same thing, ZL plus ZC, J omega L plus 1 over J omega C. I can play the game where I bring the J upstairs and I put a minus. No problem. And I notice that, look, I have a 0 real part, right? There's no resistor element in this. And I have omega L minus 1 over omega C, okay? Because both of them have a J attached. That's the imaginary part, no problem. What about the polar form? This is a little tricky, but not too bad. I put the absolute of omega L minus 1 over omega C, right? So I don't care if it's positive or negative. I'm just taking the positive version of it, right? Because if you did like a Pythagorean theorem, squared square root, it would make it positive. Okay, now what about the phase angle? Well, it's omega L minus 1 over omega C over the real part, which is 0. And you look at that, well, you go, well, that must be plus or minus 90 degrees, right? If you have a vertical line, right? If this is either pointing up or down, it's either 90 or negative 90, right? So when is it 90? It's 90 if this is positive, if omega L minus 1 over omega C is positive, and it's negative if this is negative. And I also put in included 0, right? So if you're positive or 0, you're going to be 90, and then your theta I lags theta V, or you're going to be negative 90, right? Because this is essentially, you can imagine this in the J directions either pointing straight up or pointing straight down on the complex plane. All right, not too bad. So then what? So then we have low frequency. At low frequency, what is this? What's going to dominate? At low frequency, the inductor is a short, so that's not going to dominate. That's just a wire. But the capacitor behaves like an open circuit. So at low frequency, we're not really going to get much current flow. We should get a high impedance. Let's double check from this if that is true. At low frequency, this number blows up to infinity. And so we have essentially infinity, a steady state capacitor, an open circuit. Good. What about the phase? Are we going to see a minus 90? Let's double check. Look at this. The omega becomes very, the 1 over omega becomes very large, but we have that negative sign. So we get inverse tangent of a negative number. So we're going to get the minus 90 behavior, right? And so sure enough, that makes the theta I leave the theta V like a capacitor. Fantastic, right? Okay, what about if you have omega super high frequency? So now you can see this guy goes to 0, but you're left with here, this omega. So again, that still goes to infinity. And what is that like? Well, at high frequency, the capacitor now behaves like a wire or short, but the inductor behaves like an open because it doesn't want to shake, right? Okay, low frequency, high frequency, you're not getting any current. That's kind of silly. But what about something in the middle? But let's finish this off first. So we have a high frequency inductor open circuit. Okay, what about the phase? So you have super high omega here. This goes to 0. It stays positive. So tan inverse of a positive infinity number is 90. Yep. We get theta I that lags theta V. Good, inductive. Now let's say we're going the middle. If we go in the middle, the Z doesn't have to be infinity, right? You can get somewhere in the middle. Fine. But what about a special case where omega L equals 1 over omega C, where essentially this is 0 and you get a 0 over 0? What do you get? Well, you get this. You get Z equivalent, obviously going to 0. This cancels out. That means this is going to allow a ton of current. There's a special case where this has a ton of current flowing through it. This is like a short circuit. And theta Z still is going to be 90 degrees, right? Theta I will still lag theta V in that case, right? You're just at that transition where that Z goes and then flips over and then starts going down into between quadrant 3 and quadrant 4. All right, so let's go to the simulation and check that out. All right, so we're here and we have a resistor and capacitor in series. And let's see what we have going on. We have, when it's low frequency, the capacitor is dominating because it's an open circuit and we have small I and we have current leading the voltage like a capacitor. Good. At high frequency, we have the inductor dominating because at high frequency, it doesn't like current. And we have, again, a small current. Both the low and high frequency have a small current. high impedance, and the current lags the voltage. And here we've tuned it right in the middle. So this 40 hertz frequency, this 16 microfarad, and this 1 Henry are all tuned such that omega L equals 1 over omega C. And notice we're still lagging, but we have a much larger I. We have a much larger I, okay? And it's being limited by this little 1 milliohm resistor here. I put this just so that everything doesn't explode up to infinity, right? Okay, but again, we still have current lagging the voltage. Kind of interesting, and all the equations again are right here on the top. All right, perfect. Now let's go to the last one here. So stop share, and let's go to 6. Okay, so this is where the inductor and capacitor are in parallel. And again, we do the parallel rule where you have ZL, ZC, ZL plus ZC, great. We plug in our numbers or our equations for the inductor, J omega L, 1 over J omega C, blah, blah, blah. And I can play that trick, multiply it by 1, J omega C over J omega C. That wipes out this one and this one on the lower right. And I have to now remember to do that. So I get J omega L on the top. I get 1 on the lower right, and I get J squared, which is minus, right? Minus 1 omega squared LC. Fantastic. If I want to write the rectangular form, this is easy. There's no real part. This is the imaginary part. Omega L over 1 minus omega squared LC. J, that's it. If I want to write out the polar form, well, I can write out the absolute value of this, omega L over 1 minus omega squared LC. Like I said, Pythagorean theorem, square root makes it positive. And the, what do we call it? The phase is just this over this inverse tangent. Okay. So again, this is going to slam to infinity, infinity on the inside, plus or minus, which means this whole thing is going to slam to 90 plus or minus. Okay, so if, look at the inside here, if 1 minus omega squared LC is greater than or equal to 0, that means this is a positive, which means I'm going to get positive 90 and theta I lags theta V. If this little guy is negative, well, I'll get minus 90, okay? So what do we have here? We have omega at a low frequency. Let's look at our gain at a low frequency. And before we even do this, at a low frequency, what happens? This is like a short. So the capacitor is an open circuit, so it should be more inductor dominant. Let's double check. At a low in frequency, this denominator goes just to 1, and we have 0. Yep. And so that's like a short. Good. Now what about the phase? Is it more inductor? Is it more of this? Let's double check. When omega goes to 0, look at this. We get a positive number. We get 1 minus a small number, so we get a positive number. So sure enough, that phase is going to go to 90. Theta I like theta V, inductive. Fantastic. What about high frequency? High frequency, this becomes like the short, and that becomes an open circuit. Okay, nice. So in that case, at high frequency, what do you see? We see that we get, well, this is a little bit tricky. We get this 1 kind of being negligible. So we get an omega L over an omega squared LC. Okay, and maybe I'll even say that 1 is negligible. Okay, and so we get an omega squared LC, and then what do we have? An omega L cancels, a square L cancels, so we get 1 over omega C. We know what that is. That is the impedance of a capacitor. This is more capacitive. And again, as omega increases, we get it going to 0. So both of these are behaving like a short at the very low and a very high frequency. Okay, high frequency capacitor, short, fantastic. Now we look over here, as omega goes very large with that negative number there, it definitely goes to the negative side, which means we're going to get negative 90 for the phase, very much like a capacitor, right? Theta I leads theta V. What if we get that special case again where 1 equals omega squared LC, right? Where this essentially goes to 0. Well, now the impedance shoots the roof and goes to infinity, right? But the theta Z will still be 90, right? And theta I will still like theta V. So let's check out that simulation. Okay, so share screen. Let's go to here. Okay, so we look here and we have the capacitor and inductor in parallel. And remember, at low frequency, look, you can even see it. The inductor is taking the majority of the current, and the current's lagging the voltage. And we have a large amplitude of current. Even at the high frequency, we get a large amplitude of current because this time the high frequency capacitor is taking all of the current, because the capacitor at high frequency is behaving like a short. Now look at the middle frequency where we've set perfectly 1 equals omega squared LC. Let's see what happens. Well, the current, yeah, it's lagging the voltage, but it's very small. And relative, if I scale it to the same scale as these two on the left and right, it's nothing, right? It's nearly nothing. So I hope you're seeing the nice result that it's matching the math, which is written up here. The simulation and the math are matching. The other kind of cool thing to note here is look how, it's not that there's no current at all. The current bounces back and forth inside it. And that's very much like a capacitor power factor correction example that we'll see in part B. All right. So let's just kind of compare and contrast what we got going on. When we looked at the series and parallel, notice the kind of the interplay. Here, the low and high frequency had infinite and the middle case had 0. Here, the low and high frequency had 0 and the infinite had, or the middle had infinite. That's kind of interesting. If we go to the resistor and the, let's see, there we go. So we go to the series and parallel resistor and inductor. What do we notice? We see the R here at low frequency for series, but we see that R here at high frequency for series. And we see the more inductive behavior here, right? Where this is like a high frequency inductor. It's like an open, right? Whereas here it's a low frequency inductor, steady state inductor. It's like a short. Interesting, right? And then we kind of see the same thing for the capacitor. Look at this capacitor. When we compare 1 and 2, right, what do we notice? This is a capacitor at high frequency. It's like a short, right, no impedance. But here we have a steady state capacitor open circuit, which is like an open. But in the middle here, it's the R and R. I hope you guys can see the dual of these situations. It's kind of nice. And you can either reason it out through our physics understanding or even look at the math. So you get some nice consistency from both. All right, well, I hope you enjoyed part A of this lecture, and I look forward to seeing you in part B.